Hello everyone! In this mathematics, calculus, signal processing and control engineering tutorial, we will learn how to express sine and cosine functions of the real argument or the real angle as the sum and difference of complex exponentials. That is, we will learn how to derive these formulas. In these two formulas, j is the imaginary unit and theta is the angle that is often expressed in radians. These two formulas play a very important role in digital signal processing, control engineering, and in many other fields, mainly because they can be used to significantly simplify calculations of quantities such as transfer functions, magnitude, phase responses, etc. In this tutorial, we explain how to derive these two formulas, and at the end of this tutorial, we explain how these formulas can be used to compute the coefficients of the Fourier series expansion. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot! Okay, let's start. To derive the formulas, we need to start from the Euler representation of the exponential of the complex number. For that purpose, let us consider the complex unit circle shown in this figure. The circle is represented by the dashed line. This is a circle with a radius of 1. This is the real axis. This is the imaginary axis. This point over here is our complex number. This is the vector connecting 0 to our complex number. The angle that this vector makes with the real axis is theta. The projection of this vector onto the real axis is the cosine of theta, and the projection of this vector onto the imaginary axis is the sine of theta. Theta is the angle that's often expressed in radians. Let this dot that represents our complex number be denoted by z. From this figure, we can see that z can be expressed as cosine of theta plus j sine of theta. Now, we can write this complex number in the so-called polar form. Our complex number can also be written in the polar form. The polar form of this complex number is the modulus of the complex number, that is, the distance from here to here, or the length of this vector, and the length is equal to 1, multiplying e to the power j theta. By combining this expression with this expression, we arrive at the Euler formula. The Euler's formula takes this form: e to the power j theta is equal to cosine of theta plus j sine of theta. Let us now substitute in this formula theta by minus theta. As the result, we obtain the following formula: e to the power minus j theta is equal to cosine of minus theta plus j sine of minus theta. Or, since cosine of minus theta is simply cosine of theta, and over here we obtain sine of minus theta is simply minus sine of theta. Consequently, we write minus j sine of theta. We can think of these two equations as two equations with two unknowns. The unknowns are cosine of theta and sine of theta. Consequently, by solving these two equations, we will compute sine of theta and cosine of theta, and we will derive our formulas. Let's start with sine of theta. I will take the first equation, and from that equation I will subtract the second equation. So let's do that. E to the power j theta minus e to the power minus j theta from these two equations is, let's see, we have from the first equation cosine theta plus j sine of theta, and let's see the second equation. From the second equation I have minus sign over here, cosine of theta, and over here I have minus, and this minus give plus, plus j sine of theta. Okay, now from these two equations I obtain the following: e to the power j theta minus e to the power minus j theta is actually equal to, let's see from here, 2j sine theta. Or from this equation we obtain the formula for sine of theta. Sine of theta is simply e to the power j theta minus e to the power minus j theta divided by 2j. And that's it. That's the formula for sine theta. Now let's solve these two equations for cosine of theta. Let's add these two equations. We have e to the power j theta plus e to the power minus j theta is equal to, the first equation looks like this, and the second equation is plus cosine of theta minus j sine of theta. Now, these two terms can be cancelled, and finally we obtain this expression, e to the power j theta plus e to the power minus j theta is equal to 2 cosine of theta. Or from this equation we obtain that cosine of theta is simply equal to e to the power j theta plus e to the power minus j theta divided by 2. And this is our second formula. In order to illustrate the usefulness and the application of these two equations, let's consider the following problem. Consider this function. Y of t is equal to cosine of 2 omega 0 t plus sine of 3 omega 0 t, where over here omega 0 is the fundamental frequency and t is time. And our goal is to find the Fourier series expansion and the Fourier series coefficients of this periodic function. The Fourier series of this function takes the following form. It's an infinite sum where k is the index that goes from minus infinity to plus infinity, and we are summing up these terms. ck e to the power j k omega 0 t. ck are the Fourier series coefficients. So how to represent this function in this form? That's the main question. There are two approaches for solving this problem. The first approach is to use the formula for computing ck. This is a very complex formula involving integration. However, there is a second and more elegant approach, and the second approach is to use these two formulas. And let's illustrate the second approach. Here's the idea. We can use this expression to substitute this cosine term over here. Let's do that. We have y of t is equal to, in the denominator we have 2, and in the numerator we have e to the power j, and over here the angle is 2 omega 0 t. Consequently we write 2 omega 0 t. Then over here we have plus sign e to the power minus the same angle, j, 2 omega 0 t. Then, plus, instead of the sine term, we can use this expression. Here we have 2j, and in the numerator we have e to the power, the angle is 3 omega 0 t. So consequently we write j 3 omega 0 t minus e to the power, what's the angle over here? The angle is the same, 3 omega 0 t, and we have the minus sign. And believe it or not, this simple substitution solves our problem. This is because we directly have these terms of the Fourier expansion over here, and we can write y of t like this. First we will take this term over here, and we have minus 1 over 2j e to the power minus j 3 omega 0 t. Perfect. Then we need to take this term over here, plus 1 over 2 e to the power minus j 2 omega 0 t. Perfect. Then we need to take this term, plus 1 over 2 e to the power j 2 omega 0 t. And finally, we need to take this term, plus 1 over 2j, and over here we have e to the power j 3 omega 0 t. And from this expression, we could directly read the coefficients. This coefficient over here, let's change the color, is c minus 3 coefficient. This coefficient over here is c minus 2 coefficient. This coefficient is c2 coefficient, and this coefficient is c3 coefficient. And we precisely wrote this function in this form. That represents the Fourier series expansion. And that's it. All other coefficients are equal to 0. Okay, that's all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.